The heart constellation is an image of nanoparticles called nanostars because it have star shape. In this particular image, it comes together to form a heart shape, which is, I would say, not always becoming a heart shape, but probably the cells want to give me some love. So these nanoparticles with the shape of stars, it's a tiny thing that deliver drug to bad cells, specifically cancer cells. To make the nanostars, we use 3 chemicals. The first one is ultra pure water, the second one is the gold, and the third one is a buffer, which acts as the chemical that can guide the shape to become like spiky and in the end become stars. So we use gold salt solution because how can it be gold nanoparticles without using gold, right? Here are the nanostars. There are many cells by just looking at this like circular thing. If I estimate, it's probably like 25-30 cells forming like one cluster. Breast cancer cells individually are on the size of like 5 to 20 micrometer. And the nanostars that I'm using, they are about 50 to 100 nanometers. From this point, I'm gonna inject nanoparticles into it. At first, it looks just the same, but I can see the particles by judging from like the blinking pattern. You can see that it should be about like this much bright or dark.
Here's the Nanostar drug delivery vehicle. It's time to meet the final boss, the cancer cell. The final stage of making the nanostars involves mixing them in a liquid filled with aptimers. Aptimers are a kind of single-stranded DNA or RNA that can help the nanostar bind to its target cell. Think of the aptimers as keys that are used to open doors on the cell membrane. Okay, so that's the key. Where's the door? Here's the door. So far, not too bad. So, what's the catch? Well, this is not the only kind of receptor. The nanostar should only bind to the Y-shaped receptor. These are not the only receptors on the cell membrane. Healthy cells can have up to 50,000 of these receptors, and cancer cells can have up to 2 million of them. That's right, it's not just the cancer cells that have these doors. Okay, the scene is set. Ready? Go! When the nanostar mistakenly enters a healthy cell, it doesn't do any harm, but it doesn't fight cancer either. This is a non-specific receptor. That means this is the wrong door, a dead end. For the nanostar to be effective, it has to open the right door on the right cell. Essentially, Jack's research says this: give the same aptimers to a star-shaped nanoparticle and a sphere-shaped nanoparticle. The nanostar, a lot more often than the nanosphere, avoids healthy cells, avoids the wrong doors, and successfully binds to the right receptor on the right cell. Once inside, the nanostar has a number of ways to deliver therapeutic effects, but that is a whole separate area of research.
At first, we didn't pay attention much to the shape effect on the targeting, but nanostars can improve the accuracy and the effectiveness of the breast cancer drug. They are, first, biocompatible. It's not toxic to the cell. Second, it can be used for tracking inside cells or tissues. Third, because it's not symmetric, the rotation can be tracked. If you talk about nanoparticles, you might think about sphere, like a ball, and other irregular shape, like a long rod, stars, cubes, and triangle. because we now have the capability of synthesizing all these shapes, how can we see the effect of this shape on cancer therapy, drug delivery?